Welcome back, folks. So in the last video, we talked about how to make or create the explicit equation for sequence. In this video, we'll talk about the recursive equations. And we're going to see how you can really, for some equations, you can do both. But sometimes it's actually just easier to create the recursive equation even when you can't create the explicit one. All right, so a recursive equation, if you saw before, the explicit equation is helpful because you can use it to just find the sequence, find the term in a sequence without any other information, just as long as you have that equation. A recursive equation works a little bit differently in that it tells you how to get the some term. You'll get one term based on the previous terms. Based on the previous term, and it might involve you might only need to know the one term before, or you might need to know several. And let's see examples of both of that. So let's just take a look at this equation right here. We'll start off with a really simple one, or this sequence rather. We'll start off with 5, and then let's suppose it goes to 8, then it goes to 11, 14, and so forth. Okay. So you might notice that this grows linearly. Okay. So in terms of sequences, we would say that this is an arithmetic sequence. We haven't quite got to that word to define it yet, so we won't worry too much about the language. But it looks like a linear function basically, because it grows by adding 3, adding 3, adding 3. Okay. So I could create the explicit equation if I really wanted to. Well, why don't I actually do that? So again, this is n equals 1, n equals 2, 3, 4. Okay. Now, since it's a linear function, we're so used to using mx plus b, or in this case, it would be mn plus b. But remember that b is figure 0, quote unquote, which corresponds to n equals 0. And so we would need to know what quote unquote n equals 0 would be, even though our sequence starts off at n equals 1. But we can figure that out. If we're adding 3 going forward, then to get the quote unquote 0th term, we would just subtract 3 and it would be 2. So our sequence would be explicitly written as this: a sub n is equal to 3n plus 2. Okay. So this is the explicit equation, but let's pretend I couldn't catch on to that equation. That's totally fine, because sometimes it's trickier than other times. Recursively, so again, that's the explicit equation. Explicit. You could find the 1000th term with just this equation, and you know that you're looking for the 1000th term. If I want to define the function or the sequence recursively, well, I just need to point out how it grows. And we notice it's going from it's adding 3 each time. So how could I write that? Well, I could say that, let's say, quote unquote, the current term, the term that I'm looking at right now, is the previous term plus 3. The previous term plus 3. Or, alternatively, you could write it like so. The next term is equal to the current one plus 3. And it's just a matter of perspective, right? It's like saying, I've tried this analogy several times in class. It's like saying today is yesterday's tomorrow, or you could say tomorrow is today's tomorrow. Think about that. Anyway, so how would I use like this notation then? Well, the current term, usually for me anyway, I call the current term a sub n. It doesn't actually matter which one you call it, just as long as the relationship between it and the other one makes sense. So here's what I mean. The previous term is the term that comes before the nth term. So if, for example, this is a sub 2, then the previous term would be a sub 1. And the way I would write that is a sub n minus 1. Okay? Plus 3. If I wanted to use kind of this notation or this way of describing it, then again, the current term is a sub n plus 3. And that gets me to the next term a sub n plus 1. Okay. Now, this is not actually enough on its own to describe the sequence, because there's actually a bunch of sequences that would fit this rule, right? I could start off at 0, and then 3, 6, 9, and this would fit, right? Because it's adding 3 each time. Or you might do 1, and then 4, 7, 10. So when you're talking about recursively, defining a sequence recursively, just the growth is not enough. You also need to know one other point on the graph. Or actually, technically speaking, you need only... Well, sorry. You need some starting off point. And usually it'll be the first one, but it doesn't actually have to be. It could be, the fourth term or the fifth term. But if you can give the first one, it just makes the most sense to give the first one. And we know that the first term in this sequence is 5. Okay. And this together forms your recursive equation, or you can use this one together. So let's just write out create a little table here so we can kind of see that this actually does work. So I'll say n and then a sub n. So for example, a sub 1, well, again, that's given. It's telling us we're starting off at 5. To get the second one, well, okay, so a sub 2 is a sub 1 plus 3. And so I know that that's going to be 5 plus 3, which is 8, which it should be, as we can see right here. We'll do one more just to show that a sub 3 is a sub 2 plus 3. So that's actually 8 plus 3, which is 11, as it should be. Okay, so that's how you can create an equation recursively. Again, this is an example where maybe it's not quite necessary because we can use the explicit equation. But stick around in just a minute, we're going to talk about an example where you kind of need to create the recursive equation. Okie doke, so that example will be this, and this is kind of the famous one. Actually, I don't want to use the Fibonacci sequence because everyone uses that one. I'm just going to make one up here. I'm going to go 2, 3, and then I'm going to go 6, and I'm going to go 18, and then I'm going to go, oh boy, 108. Okay? So, I don't know about you, but I don't see an explicit equation. But we can maybe try it. If we go back to kind of the common patterns, I don't really see... It's not adding the same amount each time. It's plus 1, and then it's plus 3, so it's obviously not constant. And then it's plus, 12? I don't see any pattern even in the growth. So that's kind of awkward. Excuse me. It's not geometric or exponential because it's not multiplying by the same amount each time. But yeah, so explicitly, I really don't know. But could I define it recursively? Well, let's try. So let's see. To get from 2 to 3, well, we talked about adding 1. Or I can maybe think of it as multiplying it by 2/3. There's a number of ways, but remember, look back to what we said before. When you're defining it recursively, you're going to look at kind of everything that came before it, because sometimes you're actually going to need more than just 1. Okay? That's my hint. And so, well, you should pause the video and then come back when you think you have an idea. And I'm going to assume you just did that. And here's kind of how I created the sequence. What I did was I took 6, I got 6 by multiplying 2 times 3. I got 18 by multiplying 3 times 6. And I got 108. I hope I did this correctly. By doing 6 times 18. Let me just double check here. 18 times 6 is 48 and plus... I forgot how to multiply this way. But yeah, it should be 108. Yeah, so that's how I got it. So how do I write this out then? Well, again, I could say that the current term, and sometimes it really helps me to write it out in words. is that the current term is equal to the previous term times the one before that. So I guess I could say the previous one. Notationally, well, let's see, that would be, if this is a sub n, then the one that came before that was a sub n minus 1. And the one that came before that will be a sub n minus 1 minus 1, or a sub n minus 2. Right? Again, remember that if we're going to do this, we need to know not just one starting point now, because, well, you couldn't get the third term without knowing the first two. So you need actually two starting points here. So we need to also add in that a sub 1 is equal to 2, and a sub 2 is equal to 3. So this together will give you your recursive equation for this sequence. Alrighty? So hopefully that helps. Now we know what a recursive equation is. Again, how could I do this then? You know, typically it's not super obvious always, but you know, it really just take practice to kind of build that eye for seeing how you can define them recursively. Similar, again, not too different from defining equations explicitly. It really is just one of those things that I think takes some practice. So hopefully this helped, and thanks for watching. I'll see you later.